In this lecture, we will talk about how electromagnetic interactions manifest themselves in nuclei. So, for instance, the Coulomb energy of a nucleus weakens the binding especially in heavier nuclei. It does so even in lighter nuclei, but the effect is much larger in heavier nuclei because, of course, the Coulomb energy goes like Z squared. Strong interaction energy goes only like A. So, the other place where this Coulomb energy is important, manifests itself is in the differences in energies between so-called isobaric analog states. So, these are actually states with the same, where you have the same A and the same T, but different Z. So, as we saw in the last thing, suppose you take a T equal to 1 state corresponding to lithiumate, berylliumate and boronate. Okay, then you can look for the small differences, and that you can attribute it to the Coulomb energies, and of course, if you correct for the small nuclear energy differences that come about, then you can extract a charge radius from these energies. The other place where the electromagnetic interactions are important is the electron scattering for both electric and magnetic electric charge distribution and magnetic moment distributions in a nucleus. So, their respective form factors. Electromagnetic excitation of excited states such as the giant dipole resonance, rotational states, etc., via both photoabsorption, as in the case of GDR, or in the case of low L states, such as E1 states and other E1 states and M1 states through photoabsorption, or you can have Coulomb excitation of these excited states. And you can go all the way from low energies below the Coulomb barrier, which is of the order of 5 MeV per nucleon, to a GeV per nucleon. So, if you are at the highest energy, then of course, you have an electromagnetic pulse that excites the target nucleus. Of course, it can also excite the projectile, and that has frequencies which are much larger. If you Fourier analyze the changing electric potential as a function of time, then you can excite even the giant dipole resonance by Coulomb excitation if you have GeV per nucleon beams of, let us say, lead or uranium projectiles. Then we also look at electromagnetic decay of excited. So, once you have excited a state, you can look for the photon decay, as we saw in the last lecture in the case of berylliumate. You can look for gamma rays, but there are also other ways in which that excited nucleus can decay, namely through internal conversions. So, you can have an internal conversion electron, or you can have an internal pair conversion, or even you can have 2 photon decays and so on. Okay. So, the electromagnetic decay of excited states, the kinematics is such that suppose you have a nucleus here, a nucleus with a certain Z, and it is in an excited state. So, I could call that m star c squared is its mass, and m0 c squared is its mass in the ground state, and then this of course can decay by beta or beta plus and so on. So, the beta decays let us neglect for the time being, let us only look at the photon decay. So, then this m star c squared is equal to m0 c squared plus E gamma, the energy of the photon resulting from the decay, but also a very tiny amount which corresponds to the recoil energy of the daughter nucleus. Now, since you can always go to the rest frame of the emitter, and in that case the two momenta have to cancel out. So, the photon momentum and the recoil momentum, the vector sum has to be 0. So, you can calculate the recoil energy, just P gamma squared by 2 m0, and that turns out to be E gamma squared by 2 mc squared. So, if you take a energy like 1 MeV, then and a nucleus with A equal to 100, then this recoil energy amounts to about 5 electron volts. So, the E gamma is actually 1 MeV minus 5 electron volts. Now, for all practical purposes, this might seem to be unimportant. However, if you are looking at resonance absorption, then this becomes important, because then if I have this as the energy of the gamma ray, this is the energy of the gamma ray, then the actual excitation energy is given by m star minus m, and that is just this recoil energy difference higher than the energy of the gamma ray that you observe. Okay. So, were you to actually do a photo absorption experiment, then the energy that is corresponding to, let us say, 1 MeV minus this 5 electron volt will not be enough to excite the nucleus, because when you do the reverse process, when you do photo absorption, you have to actually account for the recoil energy of the target nucleus. So, which means that you are either 5 MeV lower or 5 MeV higher than the energy that is corresponding to the energy of the transition. So, on the other hand, of course, you also have to take into consideration the fact that what is the width of this gamma ray transition. So, if you, this is just given by H cross by tau, which is of the order of 7 10 to the minus 22 MeV second by tau, and if tau has a nanosecond, if tau corresponds to about a nanosecond, this turns out to be 6.6 10 to the minus 7 eV. So, this is much narrower than the recoil width. Okay. So, on the other hand, if the whole lattice recoils, so if this decaying nucleus is part of a lattice, then you can have situations where the lattice as a whole recoils, and that happens, of course, when the recoil energy is of the order of or less than the so called phonon energies or comparable, and then you can have recoilless emission and absorption. That is actually the so called Mossbauer effect. Okay. But in most cases, when you are not dealing with resonance absorption, then of course this small shift is unimportant and you can neglect it for all practical purposes. Now, in the early days, around the early part of 1900, of course, Planck found a rationale for the electromagnetic energy to be transferred in quanta, and Einstein used this to explain the so-called photoelectric effect. Later, Compton did his experiments where he scattered a photon of an electron, and you actually were able to show that the photon also has momentum given by E by C, and that explained Compton, so-called Compton's, what is now known as Compton scattering. So, we knew that the photon has a certain energy given by H cross H nu, it has a momentum H nu by C. However, the spin of the photon was something that was not figured out early on. And in fact, the first experiment to actually demonstrate the spin of the photon as being 1 was due to Raman and Bhagwantam. So, these are the references in 1931, and they reported a better version of the experiment in Nature in 1932. So, the paper is titled Experimental Proof of the Spin of the Photon. Of course, Bose had assumed that the spin is 1 when he used his statistics to actually give a much simpler derivation of the Planck formula for the energy spectrum of a black body, the radiation spectrum of a black body. And in fact, in a private communication, as Raman and Bhagwantam report, he even believed that the spin of the photon, the projection of the spin can either be along the momentum or anti-parallel to the momentum. So, there are only 2 states, and that is because of the relativistic nature of the photon. But the spin 1 nature was inferred, was by Bose, but the experiment was actually carried out by Raman and Bhagwantam. They showed that the depolarization of photons scattered by molecules, and they in fact used the Raman scattering for that as well, is consistent with the photon having spin 1 and not 0. So, the idea is as follows: if I have a molecule with J equal to 0, it can undergo Rayleigh scattering, and this is irrespective of the polarization state of the incident photon, whether it be left-handed polarized or right-handed circularly polarized, you will still get Rayleigh scattering. However, the Stokes line, which is the Raman line, which is shifted in frequency by delta nu, so you can excite a molecule to its J equal to 2 state, and in that case, this shifted line, the so called Stokes line, that allows you to measure whether the photon has spin or not. So, what happens is that this is of course not the Stokes line, sorry, the anti-Stokes line. The Stokes line is allowed for both left-handed circularly polarized and right-handed circularly polarized. The anti-Stokes line, which is at a frequency which is higher than the incident photon frequency, where it gains energy from the molecule, which might be in a rotational or a vibrational state, that anti-Stokes line is not possible if the light polarization flips in the anti-parallel case, but not in the parallel case. So, by parallel and anti-parallel, I mean the spin of the molecule with respect to the spin of the photon. So, the depolarization is actually a measure of whether or not the photon has spin 1 or spin 0. So, this is from their paper, where they look at the depolarization on a gas, a couple of gases, as well as on a couple of liquids, and so they also measure the Stokes line in the case of the so-called QQ branch is called in the case of a liquid. So, they observe the depolarization as well there, and from if the photon spin is 1, then you get a depolarization which is given by this number here, whereas classically it should have been much smaller. Okay, and similarly for this molecule benzene. And in the gas also they observe the depolarization effect, and this is so for so as I said, of course you can have molecules in j equal to 0, j equal to 2 state. So, what I said for the j equal to 0 state for the Stokes line, that there is no difference between LS left-handed and right-handed circularly polarized, but there is a difference if you go to the j equal to 2 state for the Stokes line as well. Okay, so if you do that, then again in the gaseous phase you observe a depolarization which agrees better with the observation if the spin is 1, and if the spin is 0, what you expect classically, then of course you get a much very different depolarization, and so this agrees with the fact that the photon has spin 1. A very different way of actually converting the angular momentum in a photon of circularly polarized photons to a mechanical device, that was done by Beth, and this was done in 36, a few years later. So, the title of this is Mechanical Detection and Measurement of the Angular Momentum of Light. So, this is a schematic of the setup. So, you have light which is circularly polarized in a half wave plate, and then it goes and interacts with a plate here, to which it transfers angular momentum, and then when it comes back it actually reverses the polarization, and then this can be done a couple of times, so that you get an effect which is 4 times that in which it was just absorbed. And so you do that with you impart a torque to a torsion pendulum. So you actually give this torque in a direction opposite to the restoring torque. So you actually decrease the amplitude where this light to have an angular momentum, and so this is the effect that was seen. So the amplitude actually decreases at a certain frequency of application of this light, and it also increases with temperature. So if you increase the temperature of the filament here, then of course the light intensity increases, the number of photons that you are dealing with increases, and so the angular momentum that you are dealing with also increases, and therefore this torque, the so-called light induced torque, it actually increases, and so it goes in the right way, and it goes in a way which is very different from what you would expect classically, and so this was again a very direct measurement that photons actually carry angular momentum. Okay. Now we come to the other aspect of when you have gamma ray decay or you have electromagnetic decay, you can not only have photon emission, but you can also, and we will discuss that a little later, the photon decay, but let us discuss the internal conversion electron emission. So, if you have an excited nucleus, it can decay to a positive ion of that same nucleus. It could also be in a excited state, a lower excited state, and then with the emission of a electron. This is called the conversion electron, and the conversion electron energy is just given by the excitation energy. So let's say EI minus EF minus the binding energy of this electron. So, this N can be 1, 2 and so on, K, L, M, M shells. So, it can be BK, BL and so on. I should just point out that this conversion is actually a kind of misnomer, because it is not photon emission followed by the ejection of atomic electron. That would just be the photoelectric effect. This is not that. The nucleus makes a transition, but a photon emits. So, the photon that is emitted, the photon that is involved in this is actually a virtual photon, okay, and then you get ejection of the atomic electron. As you can guess, if you want to eject an electron, it's easier to eject a K shell electron, because that has the maximum overlap with the nucleus, and therefore when a nucleus de-excites, if I have a K electron wave function there, that is the easiest to eject. The L electron has of course a lesser probability to exist at the nuclear site, and so S electrons are the one which are most often ejected. They have a higher probability for emissions, and if you actually convert this, how many of these electrons come out as compared to how many gamma rays come out, then this you can write this down as a ratio, and this is called the internal conversion coefficient. You can define it for K shell electron, L shell and so on. That would just be the number of these conversion electrons divided by the number of photons that you get in such a transition. It is also important to point out that just as higher L electrons have lesser probability of going through this conversion process, the 2s electron has a smaller probability for emission, because of course the probability that it exists at the nucleus goes roughly like 1 by n cubed. So, it is 8 times less probable for a 2s electron to be there at the nuclear site as compared to the 1s electron. Okay, and then the total internal conversion is of course the sum of the conversion coefficients for the K electron, L electron and so on. Of course, if energetically it is not allowed to eject a K electron, as might be the case if the transition energy is lesser than the binding energy of that K electron, then of course you can only have L electron emission and so on. Just for getting some feel for the numbers, the momentum of a 100 keV conversion electron for a medium mass nucleus is of the order of 300 keV by C, whereas it is about 100 keV by C. Of course, this is independent of the Z, because we already taken care of the binding energy. So, this is a 100 keV conversion electron, and that you can compute given the mass of the electron, that is about 300 keV by C. Whereas for a photon, this momentum corresponds to about 100 keV by C. The electron, conversion electron has a momentum 3 times than that of the photon, of course for this energy. So, typically the spectrum of electrons in beta decay and internal conversion, as say for instance in 203 lead, which decays by beta minus emission, and the maximum energy is 214 keV. So, it mainly goes to the excited state, and then that decays by 279 keV transition. So, that can both emit a gamma ray as well as a conversion electron, and so if you looked at just the electron spectrum, then you would have beta decay electrons limited to about 214 keV, but you would have K conversion electron riding on this, peak riding on that. The L binding energy is smaller, so that goes actually beyond the endpoint energy of the beta decay, and then the M is a small shoulder on this L conversion electron part of the spectrum. Okay. Now, this is a somewhat busy plot here, but suffice, I'll come to what I just wanted to indicate. Maybe I should get a better figure for the plot that I will put in the PPT file later. The conversion coefficient is higher for low energy electromagnetic transitions and for higher multipolarity electromagnetic transitions. Okay. So, if you look at low energies, the conversion coefficient is high. As you increase the energy, the conversion coefficient drops. So, this is for the electric transitions. So, this is E1, E2, E3, E4. So, E4 has the larger conversion coefficient as compared to E1. So, this is E4, this is E3, E2, and this is E1. Okay. And this is Z equal to 60. So, this is of the order of, so this is 10 keV, 100 keV and 1 MeV. Okay. So, it shows a bump because of course, you have the K shell electrons contributing here sizably to the conversion and L and so on are contributing in this part of the energy of the transition. So, we just, if you remember the earlier slide, the momentum of the conversion electron is higher compared to that of the gamma ray. And so, of course, as you go to higher and higher transition energies, this overlap tends to decrease. So, the conversion coefficient becomes smaller and smaller because you have to transfer this energy in the form of a moving electron. And okay, so in any case, the overlap also is an important factor, overlap of the electronic wave function. So, all of these factors contribute to leading to a situation where the conversion coefficient decreases with energy of the transition. And of course, if you have a higher multipolarity, then if you have the coefficient increases because it is easier to take away angular momentum with a massive particle like the electron as compared to that of to a photon. So, in fact, for a okay, for this it is a factor of 3, that is as we saw there. Okay, so this is taken from this reference. As you can see, the conversion coefficient, maybe you can't see it from this graph, but I can, if you believe me, the higher Z elements have a higher conversion coefficient for the same energy. So, let us take this 100 keV, this is higher for Z equal to 90 as compared to Z equal to 60. And there are various ways of measuring these conversion electrons, and these are usually measured by magnetic spectrometers in conjunction with silicon detectors, or they can also be measured by plastic scintillator arrays, but you have to have delta E telescopes to emphasize the electron signal as compared to the photon or neutron signal that you might have as a huge background sometimes. So, what is shown here is a figure or figures corresponding to a so called orange spectrometer, a mini orange spectrometer using permanent magnets. So, electrons are produced here and they can get detected here or vice versa, and they get bent by the magnetic field between these two pole pieces, and there are 6 such pole pieces, and so it is like a orange. That's why it's called a orange spectrometer, and this is a this is data taken from one of the proceedings of the DAE symposium, where they have used this mini orange using spectrometer, electron spectrometer built from permanent magnets. You can get very strong magnets, and therefore they can bend these electrons up to about an MeV energy or so onto a detector. And so this is the side view of this is the sort of view at an angle, and this is the top view of the mini orange spectrometer. So, the toroidal magnetic field basically is used to transport electrons, and typical momentum resolutions are of the order of 1%. You can do that with, of course, field that you can vary and then you can count it, or you can use this just to transport onto a silicon detector which has anyway a higher resolution. So, it can be done in both ways, and typically the momentum resolution is of the order of a percent and transmissions of the order of a few percent to 10%. You can also use a solenoidal spectrometer which has an axial magnetic field and which transports electrons through their helical paths onto a detector, which could be a single or multi-element silicon detector. And there, of course, the resolutions are of the order of 2 to 3 keV at about an MeV, and you can have very high efficiencies. And so you can make the solenoidal spectrometer either from a room temperature coil at room temperature, copper coil at room temperature, passing a current through that and getting this axial field, or you can have a superconducting solenoidal spectrometer. So this is schematic of a solenoidal electron spectrometer with coils at room temperature, which shows that you can have a source here, and then these electrons move in helical trajectories onto a silicon detector here, and these are the coils that make that magnetic field. This is what is shown is a detector here, a germanium detector. So you can do gamma ray electron coincidences. Another picture of a spectrometer, not of the mini orange type, it's pretty big. As you can see, this is the beam line, and then there's a place where you can put a target. And here the magnetic field is varied by changing the current in the exciting coils, which and then you can actually, so this is a single channel kind of instrument, whereas the other one, mini orange, is a multi-channel instrument where you accept a broader range of momenta, whereas here you focus these electrons onto a detector down below, and you have to actually change the current so as to change the magnetic field, and field by field, so you can scan the momentum spectrum of the electrons. So this is a better view of that, same picture, but then it shows a detail of the 6 gap orange spectrometer. So you have these 6 gaps. So this is taken from this reference of Sigban, and you have 6 gaps. This is a top view of the spectrometer. This is a side view of the spectrometer. So electrons come in from somewhere here, they get bent and they get focused onto a detector here, which can be a plastic scintillator, or you can have even a silicon detector there, it depends. The other process that occurs is the internal pair conversion. So you can have, if the excitation energy is more than twice the rest mass of the electron, then of course you can also have E plus E minus emission, and then you have to measure the electron and the positron. And if you neglect the recoil energy, then by detecting these two particles, you can actually get the transition, you can measure the intensities and so on. So for instance, in oxygen 16, you have this 0 plus state at about 6 MeV, and this where you have to excite this would decay either by 2 photon emission or by E plus E minus emission, okay. Because of course you cannot emit a single photon, because a photon carries spin 1, so you cannot go from a 0 plus to a 0 plus transition by 1 photon, but you can go via 2 photons, and of course by E plus E minus emission. The conversion electron process in this case is very small. You can neglect it actually, because the energy is so high and the Z of the nucleus is so small. So this is an example of an electron-positron pair spectrometer. So you have a large plastic scintillator, and you have a detector here which measures the delta E. It can either be a plastic or it can be a gas detector, such as a multi-wire proportional counter, or it can be a very thin silicon detector which is position sensitive and so on. So you can actually measure the angle of each of these electrons or positrons and then reconstruct the sum energy spectrum with cuts on the angle and so forth. This becomes less sensitive to, as I said, photons and neutrons. And so this is an example of a Hungarian group which has measured the pair spectrum at this resonance energy. Energy width of this pair spectrometer is about 0.8 MeV at about 17 MeV. So it's sort of 1 part in about 20, so about 5% energy resolution. This is good enough for some measurements. This is the efficiency plot. If you have isotropic emission of E plus E minus, you can see that this is of the order of 1.5% or so. The electromagnetic decay of excited states, of course, the way you do it is the electromagnetic Hamiltonian involves the scalar product of a nuclear current J and the electromagnetic 4 vector current which is denoted by A. Then it is expanded in terms of multipoles, and in fact the photon field can come from electric or magnetic multipoles of each type. So, we have E lambda or M lambda multipole contributing, and for transition energies of the order of MeV and R of the order of 6 Fermi, which is a medium sized nucleus, the contribution from a higher multipole goes down by k gamma r squared. Okay, so this k gamma r is less than 1, so square of that is so. Because this is due to the small r behavior of the corresponding Bessel function that comes in. Also, magnetic contribution, it turns out, are V by C times smaller than the corresponding square time smaller than the corresponding electric multipole. So, a full derivation of course is not going to be given here. This is there in many textbooks, and only the final Weisskopf estimates along with the reduced transition probabilities are given. So, this is the reduced transition probability for the electric multipole and for the magnetic multipole, and this is the transition probability is in units of second inverse. I should have put these units here. So, let me put it here. This is in terms of second inverse, and where the photon energy is in terms of MeV, and of course A stands for the mass number. Okay. So, as you can see, the transition probability goes down drastically as the multipolarity increases. So, of course, E1 transitions are faster than E2, and similarly E2s are faster than E3. However, if for some reason E1 is hindered or sometimes even more or less forbidden, then the E2 transition can be there. So, for instance, if you take a 2 plus to 0 plus, then of course angular momentum selection rules tell you that E1 is not possible, but then the E2 is the most prominent one, and so on. And then depend. So, there are selection rules which you have to look at also. So, for instance, the selection rules for electromagnetic transition, since the photon spin parity is 1 minus. Why is it 1 minus? Because of course it is represented by a vector field A, and that changes sign if you change parity. So, the gamma decay from a 0 plus state to another 0 plus state is forbidden by angular momentum conservation. This I already mentioned before. For E1 transition, since the E1 operator changes sign under the parity operation, the initial and final parity, the product has to be minus 1. Similarly, for a E lambda transition, there has to be minus 1 to the power of lambda. So, for instance, if for a E2 transition, minus 1 to the power of 2, so this is just plus 1. So, these two parities, so it has to be either from negative parity to negative parity or positive parity to positive parity. For M1 transitions, the corresponding operator does not change sign under the parity operation. So, this product is just 1. For higher multipolarity, of course, it is minus 1 to the power of lambda plus 1. So, okay, in summary, we will of course have reason to talk about these as we go along, but as far as this lecture goes, I should summarize it by saying that we have looked at electromagnetic decays of excited nuclei by one photon, convergent electron, and pair conversion. We have still not looked at two photon decays, for instance, and they have an interest in their own right. We will see that later, sometime later. This is again a typo. We have seen that the selection rules for so-called electric and magnetic transitions. Okay. So, of course, you might have mixed transitions as well. You can have, for instance, a mixed M1 E2 transition, and so depending on the amplitude, you get a mixing ratio and so on. So, I come to the end of this lecture. Thank you.